Imagine standing on the edge of a vast, jagged cliff, the wind pressing against your chest as you look out over a canyon so immense that the far side dissolves into haze. You know something is out there, something real, something extraordinary, but there's no bridge, no ladder, no path forward, just distance, just emptiness, just the quiet realization that wanting to cross doesn't mean you can. That's exactly where humanity stands today. We are staring out into the cosmic abyss, toward the nearest star system, knowing it exists, knowing it's within reach in a cosmic sense, and yet completely unreachable in any practical one. That star, Proxima Centauri, sits just 4.24 light-years away. On the scale of the universe, that's incredibly close, practically next door. And still, we can't get there. Not with the technology we have. Not with the technology we're close to building. Not in your lifetime. Not in your children's lifetime. Maybe not ever. And the reason why isn't just about better rockets or more powerful engines. It's not about funding or ambition or political will. The real reason is far more unsettling. The universe itself may not allow it. This isn't a story about engineering limitations. It's a story about running headfirst into the fundamental laws of reality and discovering they don't bend. So in this deep dive, we're going to unpack why interstellar travel between stars, is so brutally difficult. We'll start with distance, because our brains are terrible at grasping it. Then we'll look at speed, and why even our fastest machines fall hopelessly short. And finally, we'll confront the deeper truth. Even if we solved propulsion, the universe has other barriers waiting. Let's begin with something familiar. The moon. It orbits Earth at an average distance of about 384,000 kilometers. That sounds far, but in cosmic terms, it's right next door. Light, the fastest thing in the universe, travels that distance in just over a second. When humans first traveled there during the Apollo missions, it took about 3 days. 3 days. That's a journey you can comprehend. That's human scale. Now step outward to the sun. It's about 150 million kilometers away. Light takes a little over 8 minutes to reach us. If the sun vanished right now, Earth would keep orbiting nothing for over 8 minutes before we even realized something was wrong. Already, things feel less intuitive, but these distances are nothing compared to interstellar space. Proxima Centauri is about 40 trillion kilometers away. 40 trillion. That number is so large your brain probably just blurted into abstraction. So let's shrink things down. Imagine Earth as a small marble sitting on a table. On that scale, the sun would be about 30 meters away, roughly across a large room. Now where is Proxima Centauri? Not across the room. Not across the building. It would be about 8,000 kilometers away. That's like placing your marble Earth in New York, your sun somewhere across a field, and then putting the next star system all the way in Tokyo. Between them, nothing. No stepping stones, no shortcuts. Just empty, silent space stretching across a planetary scale void. That's the canyon we're trying to cross. So naturally, the next question is, how fast can we go? Humanity's fastest spacecraft to date is the Parker Solar Probe. At its peak speed, it reaches about 700,000 kilometers per hour. That's fast enough to circle Earth multiple times in under an hour. It's fast enough to travel from London to Sydney in less than 2 minutes. That sounds incredible, until you aim it at a star. At that speed, reaching Proxima Centauri would take over 6,000 years, 6 millennia. To put that in perspective, 6,000 years ago, human civilization was just beginning to experiment with writing. The pyramids didn't exist yet. Entire empires had not yet risen or fallen. If ancient humans had launched a probe at that speed, it still wouldn't have arrived today. And here's the catch. The Parker Solar Probe only reaches those extreme speeds by falling toward the sun, using its immense gravity like a slingshot. A spacecraft traveling outward, away from the sun, wouldn't have that advantage. It would be slower, much slower. Let's bring it down to something even more intuitive. Imagine you draw a line on the ground representing the distance to Proxima Centauri. You shrink it so that 1 meter equals 1 light year. That means the total distance is just over 4 meters. You could walk it in seconds. But now imagine each step you take represents 1 year of travel at the speed of Voyager 1, the farthest human-made object ever sent into space. To cross those 4 meters, you'd need to take over 73,000 steps. That's not a walk. That's a lifetime stretched into impossibility. Voyager 1, launched in 1977, is moving at about 61,000 kilometers per hour. At that speed, it would take over 73,000 years to reach Proxima Centauri, and it's not even heading in the right direction. So the obvious solution seems simple. Go faster, build bigger engines, carry more fuel, push harder. But this is where physics sets a trap. There's a fundamental equation in rocketry called the rocket equation, and it's brutal. In simple terms, it says this: the faster you want to go, the more fuel you need. But fuel has mass, and that mass requires more fuel to accelerate, which adds more mass, which requires even more fuel. It's a feedback loop that spirals out of control. To accelerate a modest spacecraft to even 10% of the speed of light using chemical rockets, you'd need more fuel than exists on Earth. Not more than we can store, not more than we can mine, more than physically exists on the entire planet. At that point, rocketry doesn't just become impractical, it becomes meaningless. So engineers and scientists have looked for alternatives. Ion drives, for example, use electric fields to accelerate charged particles. They produce very little thrust, but they can run for long periods, slowly building up speed. Nuclear propulsion systems could, in theory, double the efficiency of chemical rockets by using a reactor to superheat hydrogen and expel it at high velocity. And then there are more extreme concepts, like nuclear pulse propulsion, where a spacecraft rides the shock waves of controlled nuclear explosions. These ideas are bold. Some are even plausible. But they all share the same limitation. Even in the best-case scenarios, they only reach a fraction of the speed of light. At 5% of light speed, a journey to Proxima Centauri would take around 85 years. At 10%, about 40 years. Better than thousands of years, but still longer than most human lifespans. And none of these systems exist in a form capable of carrying people. They're concepts, experiments, possibilities on paper. But even if we solved propulsion, completely solved it, we'd still face the most unbreakable rule in physics. Nothing with mass can reach the speed of light. As you accelerate closer to light speed, the energy required to go faster increases dramatically. Not linearly, not exponentially, infinitely. You could harness the total energy output of a star, and it still wouldn't be enough to push a spacecraft with mass to the speed of light. That's not a technological barrier. That's a law of reality. So interstellar travel will always be slow. Painfully slow. But the problems don't stop there. Because even if you had a ship capable of crossing the distance in decades, the journey itself would be lethal. Once you leave Earth's protective magnetic field, you're exposed to cosmic radiation, high-energy particles traveling near the speed of light, produced by supernovae and other violent cosmic events. On Earth, we're shielded from most of this radiation. In deep space, there is no protection. Over time, that radiation damages DNA, increases cancer risk, degrades cognitive function, and weakens the body in ways we still don't fully understand. Shielding helps, but it introduces its own problems. Dense materials can actually create secondary radiation when struck by high-energy particles. In trying to block the danger, you can make it worse. Then there's microgravity. In space, without gravity pulling on your body, muscles weaken. Bones lose density. The cardiovascular system changes. Vision can degrade. Astronauts on the International Space Station exercise for hours every day just to slow the damage, and they're only there for months. Now imagine decades. The human body wasn't built for that. And even if you solved that problem with artificial gravity, you'd still face something even harder to engineer: the human mind. Interstellar travel would mean isolation on a scale we've never experienced. Communication with Earth would take years. There would be no real-time contact, no help, no support, just silence. Psychological studies show that even short-term isolation can lead to depression, anxiety, and cognitive decline. Now stretch that to decades or generations. Because one proposed solution is the idea of generational ships, massive spacecraft carrying entire communities, where the descendants of the original crew would be the ones to arrive. But that introduces another problem: human society itself. Cultures change, languages evolve, beliefs shift, systems collapse. Maintaining a stable, unified mission across centuries inside a sealed environment may be one of the most difficult challenges of all. And then there's the environment of space itself. It may look empty, but at high speeds, even tiny particles become deadly. At a significant fraction of the speed of light, a grain of dust could hit with the energy of an explosive. A pebble could destroy a spacecraft. And at those speeds, you wouldn't see it coming. You'd be outrunning your own ability to react. Every second of the journey would be a risk. So when you put it all together, the distance, the speed limits, the energy requirements, the radiation, the biology, the psychology, you start to see the full picture. It's not just hard to reach another star. It may be fundamentally beyond us. There are theoretical ideas, wormholes, warp drives, that suggest shortcuts through space-time might exist. But they require forms of matter and energy we've never observed, in quantities that may be impossible to achieve. They're fascinating, but they're not solutions. At least, not yet. So where does that leave us? Strangely, not hopeless. Because while we may never physically cross the gap between stars, we can still explore them in another way. We can observe. We can analyze. We can point our telescopes at distant worlds and study the light filtering through their atmospheres. We can search for chemical signatures of life. We can map planets we will never visit. Our bodies may be confined, but our understanding isn't. And maybe that's the most remarkable thing of all. We are a species capable of comprehending a universe far larger than we can ever physically explore. We can stand at the edge of that cosmic canyon, not able to cross it, but able to measure it, to understand it, to know exactly how vast it is. And in that understanding, there's something profound. The stars aren't going anywhere. They've waited for billions of years. And even if we never reach them, the fact that we looked up, asked the question, and understood the answer, that might be enough.